All right, it's recording. All right, team. So just clarifying again, 5A, 5B, 5A, exercise 5A is notation. So you just need to know how to use notation, which you have to do pretty much all of chapter 5. So that's why you can combine it with 5C, 5D. 5B is domain and range. So that's where I was talking about X values and Y values. But the best way to explain it is with graphs, and 5C and 5D has graphs. So I'm going to combine your understanding of domain and range within 5C and 5D. Okay? And then if you need extra practice, we can then look back at that exercise. All right? Let's have a look now. 5A, 5B is partially done. 5C, what it is the difference between a function and a relation. Relations are literally simply a set of coordinates. That's all it is. So an example would be, this could be a relation. So if you plotted on Desmos, on your CAS calculator, you plotted 1, 2, the point -12, 4, 33, -6. That is a relation. So I can draw on the axes and I can do this. 1, 2, 3, 4. That's a relation. Some relations, though, sometimes there's a pattern to it. So, for example, what kind of relation does that look like? Or what have we seen? What is that familiar to? What kind of pattern are we seeing? Linear. And it just so happens it fits in one of the things I'm going to tell you to write down here later. That is a function. Just so happens to be a function. But every set of coordinates is called a relation. Okay, so you can have a quadratic, which is like that, and it happens to follow one of the definitions of what a function is. So that relation is now considered a quadratic function. Whereas a square root, remember when I showed you a square root, you could have a bunch of coordinates that look like this. There is a pattern there. And that pattern is a square root, but we call this square root relation because it does not fit the definition of what a function is. So the question is, what is a function then? A function is for every x coordinate, there is a unique y coordinate. Okay, so write that down. Now, if you're thinking about what I'm saying there, why is this not a function? You can see that if I picked an x coordinate, let's say I picked this point here in green. That point, let's say x was 4. And let's say this is a square root relation. So square root, what's the square root of 4? 2. So that means this point could be 2, 4, 2. So you've got a 4. So for every x coordinate, there should only be one unique y coordinate. But what you can see in this graph here is that at 4, I can have 2, but we also know that the root of 4 is not just 2, it is also, so it's plus and minus. So what that means is that when you look down, there is also a second coordinate right here, where it's still 4 again, but then the y value is -2. This means that for one x coordinate, so if you think of it as a machine, so this is why I drew the picture down here, if you put in x is equal to 4, and the machine says, I'm going to square root whatever x is, I don't get one answer. I actually ended up getting 2 answers. You can get 2 or -2. That's not a function. As soon as you get 2 answers, that's not a function. That's called a relation. Okay, so that's how we can see it on a definition basis. That is why this is called a square root relation. And that's why when you learnt exercise 4D, I think it was, you only did the top half. See, why you only did the top half is because if you only had the top half, there's only 4, 2. So that means for every x coordinate, there is one unique y value that sticks to it. There's not 2. That's why a linear equation, so if you ever think about a linear equation, every x value, whatever the x is, there's only one unique y value. That's why it's called a linear function. What about a quadratic? So if you think about a quadratic, same thing. If I picked 2, there's only one value for the y. So 2 squared is 4, and I know that negative 2 squared is also 4, but they never said you can't have double x's. They just said that you have to have only one y. So here you've only got 2, 4, so the one y value, and then here's negative 2, 4. You got 2 different x's, but only one y. So as long as you have one y value that comes out of the machine or function, then we call that a function. If you get more than one, we call that a relation. Does that make sense? That's pretty much what exercise 5C is. So 5C is just saying, do you know what a relation is and what a function is? And by definition, relation is just any number of coordinates. A function is literally when you only have every x has only one y value. And the best way to describe it is I think of a machine. Whatever you put into it, it better only come out one. Should only be one value. So here's the machine for a quadratic function. If you had y equals x squared, if I put in x equals 2, it only spits out 4. Doesn't have another value. Just one comes in, one comes out. That's when it's a function. When you have two things that come out, it's a relation. So here's a picture of two possible relations that you already know. That's called a square root relation. This is a circle relation. These are relations. These are functions. And you'll hopefully see the pattern here that if I picked 5, you can see that there's only one unique y value. There's only one y value that corresponds to that one point. This one's the same thing with quadratics. If I pick 3, there's only one y value that corresponds to that point. Whereas these two, if I pick 10, you can see that when x is 10, there are actually 2 points where they can have an x coordinate of 10. That's a problem. That means there's 2 different y values. There's a y1 here, and then there's a y2 there. That's a relation. That means for this machine, when you put in 10, you get 2 different y values. Same thing with the circle. See, with the circle, if you look at the circle, if I put in 1, there's a point 1 on the graph, and that gives you one y value. But with the same x equals 1, there's also another point on the circle, whereas x is also 1 again. But you have a different y value. So that's 2 y's for 1 x. Okay, so that's why we're saying it has to be 1 x for 1 y. Does that make sense so far? Now there is a cheap, quick way to determine if something's a function or not. And that's what you learn in 5C and 5D. If you flip over to the next page, I'll tell you the little secret. So that quick test, this section here. If you draw a vertical line down, it is used to test if it is a function. Write that in. So if you want to know if a graph is a function or not, we use what they call a vertical line test. Okay, so if you draw a vertical line, which makes a lot of sense. If you look at the diagrams that I just drew before, you can see that actually if you did a vertical line, it makes a lot of sense here. So I'll show you again. I'll go back. Can you see how in each one, if I did a vertical line for this one, it only cuts once. So it means there's only one y value that cuts it. Same thing with this one. If I draw a vertical line, no matter where I draw it, it's always going to cut once. So all these are functions. But if I do a vertical line test over here, see vertical line test, cuts twice. If it cuts twice, it means there must be 2 y values for the one x value. Because that vertical line is when x equals to a certain number. That's your linear lines. Vertical lines are x equals. So you only got one x for 2 y's. So if I do a vertical line test here, that's not a function. That has 2 intersections, so that implies there's 2 y coordinates. So right there, vertical line test will test if it's a function or not. That's all it does. If you do a vertical line test, crosses twice, it is not a function. So let's do a quick one. You scroll down to the next page. Let's see if you can pick out which ones are functions. Now I'm going to test you. I'm going to call out a couple of students. So do vertical line test in your head. Let's go with Sion. Is A function or not a function?
It is a function.
It is a function. Vertical line test, crosses once. Yes, it is a function. Next one, B, Numafi. Is this a function or not a function? Not a function. Vertical line test, crosses twice. Not a function, it's a relation. Let's try the next one. C. Let's go with Luke. It is a function. I do a vertical line test, crosses once. There's only one y value to it. So for every x, there's one y. This is a function. Milena, D. Is it a function or not a function? It is a function. Do a vertical line test, crosses once. It's a function. Kai, E. Is this a function or a relation? It is a relation. Vertical line test, crosses twice. That's a relation. What about F, Lucky? Function, correct. Every vertical line test, no matter where you draw, it is one. So it's a function. G, Mete. Function. Vertical line test shows only one intersection. H, Zoe. Relation. Does that make sense so far? That's 5C. Okay, so 5C is just knowing, is it a relation or is it a function? What gets tricky is sometimes if you're just looking at coordinates because you can't see the picture. So there's a little hint. How do you know when it's a function or a relation? Say the first one. You have to now try to picture this in your head. Is this a function or a relation? How do I know? It's a relation because of the coordinates. Which coordinates are you thinking? Because you need to, if you, no? All right, 2 and 4 and 4 and 4. So this is where it gets tricky. I want you to picture this now. I'm drawing it. 2, 4, so 2 is here, 4 is over here. So 2, 4 is there. And then 4 and 4 must be over here. Now if I did a vertical line test, is that a problem? No. That doesn't cause a problem if you have double y's. When is it a problem? Is when you have double x's. Kind of like the one I showed you up here before. See, why is this a problem? You have double x's. So how do you know if something's a function in coordinates if you can't see the picture? Look for ones with repeated x's. Anything that has repeated x's is likely meaning you're going to get 2 different y values. Because for the 1x, you get 2 y values. So don't look for the y's. That's why it gets a bit counterintuitive. When you look at this one, all I'm looking for right now is, where's the repetition in the x's? This one has a 1, has a 2, has a 4, has a 3. They're all different. So it is going to be a function. Okay, so it's a function because there's nothing that doesn't fit the idea that for every x value, there is a unique y value. It fits that. 1 has a 3, 2 has a 4, 4 has a 4. But even though you have 2 of the same y values, only one y value. It's 2 different x's. That's okay. And 3 has a 6. So that still fits the definition of function. So yes, first one is a function. Using what I just taught you, which one is not a function? Can you see it? Which one's a relation? Hands up if you have a clue. There's not enough coordinates for these ones. You have to picture these all. That's okay, actually. I just realized you have to know these graphs. So quadratic, clearly function. Vertical line test is a function. Cubic, you probably haven't learnt that yet, so I can picture it, so I know it looks like this. You may need to use your CAS to picture these ones, actually. Is this a function or a relation? Function as well. Okay, so you can see it's 1, 3, x has a 1, 2 has a 4, 3 has a 6, 7 has a 9. It's definitely a function. Every one of them is different. So for every x, think of the machine. I put a 1, I only get 3. I put a 2, I get a 4. So they're all different. Each one is a different value. Okay, as long as it's 1 for 1, it's okay. All right, team, so that's exercise 5D that I'm showing you right here. So if you can tell if it's a function or a relation. What I haven't taught you is, let's go back. Go back to this page, yep.
Wait, are you going to explain what one-to-one means?
So 5C was just to know what a relation and a function is. So now you have an idea of what it is. Then 5D, you need to be able to tell the difference between the types of functions. There are 4 types of relations, and only 2 of which is a function. Now, the way I like to teach my students is, you know how your coordinates are in x and y? What this is saying is 1x, if you put into 1x into the machine, you will get 1y coming out. This one's saying if you put many x's, so many x's, you will get 1y coming out. This is saying that you put 1x and you will get, so if you put 1x, you will get many y's. Okay, so that's what that's saying. So 1 to many means 1x coordinate will give you 2 or more y values. And this is saying when you put many x's, you get many y's. Now, just based on the definition of function, which one of these is definitely a function then? Think about the definition of a function. For every x value, there must be a unique y value. Which one of these will likely give you a unique y value, Ben? First one, because it's 1x for 1y. That's a 1-to-1. That is a function. So right here, that's a function. There's one more. Yeah. There's one y, because remember the function just says for every x. It didn't say that it had to be 1x. It just said every x, there should be only one unique y value. And there is. So you can have many x's, but as long as only one y value comes out, that's a function. So the first two is a function. Whereas the next 2 is considered a relation. I mean, they're all relations, but remember, not all relations are functions. So I gave you a quick test before. The first one, a vertical line test. Test as if it's a function. You will need to know this when we get to inverses. Okay, so horizontal line test will test if it is a 1-to-1 function. And the logic makes a lot of sense here. So I'm going to go back to, once you copy that notes down, I'm going to go back to the pictures so you can see what I mean by a horizontal line test, okay? So have a think, write it down. It's 5C, 5D. All you're doing is just identifying a relation versus a function.
Do we write 1-to-1 function or 1-to-1 relation?
Function. Because they're all relations, but within these relations, there's only 2 that's specifically a function. Yeah. So there are 4 types of relation, but 2 of which we call function. All right, let's have a look back at this graph here. Remember how I said for every x value, you did a vertical line test. You told me this one's a function, and you told me this was also a function. It's true. But they're very different graphs. See, if I did a horizontal line test, which I'll do in blue, this still only intersects once. So it means that literally, for every x value, there is only 1 for 1. So that's what it means. When you say 1x for 1y, clearly a linear graph is a 1-to-1. This is a 1-to-1 function. Whereas this one, yes, it is a function. For every x value, there is one unique y value, but it's not 1-to-1. See, if I did a horizontal line test, this shows me that there are 2 x values for just one y value. Can you see that? So x1, x2. There are 2 x values just for the one y value. So this is called many-to-one function. Because function says as long as you only have one y, and I do. I only have one y. Every line that I draw, there's only one y value, but I may have 2. So that's called a many-to-one function. The reason why you want to know if it's a many-to-one or a 1-to-1 is because when you do exercise 5F inverses, you can only have an inverse if it's a 1-to-1. You can't do an inverse when it's many-to-one. That's why the inverse of an x squared is the square root, but that's not a function. The square root actually looks like this. Because if you do the inverse of that graph, that's what you end up getting. So when you do a many-to-one, what's interesting is it becomes a 1-to-many. It literally swaps when you do the inverse. And that's why this is not a function. So later on exercise 5F, you need to find inverse functions. You have to first test, do you have a 1-to-1 or a many-to-one? Okay, so that's for 5F. Okay, but just as a sort of FYI for today, all you need to understand is Is it a function? How do you know? Do a vertical line test. If you want to know if it's a one-to-one, because there's two types of functions, do a horizontal line test. If it crosses once, it's one-to-one. Crosses twice, it's a many-to-one. Okay? Let's try this one now. Let's go back to this one. So you told me these are functions. I'm going to highlight them. Function, whoops. I'm going to go back to this one. Where's my pen? Where's my pen? There we go. You told me that's a function, 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 function. Okay, so you got 1, 2, 3, 4, 5. Let's go. Is a one-to-one function or is it a many-to-one function? Which one is it? Many-to-one. How do you know? Horizontal line test. Crosses twice. So this is a many-to-one. So I do MO. Okay, so many-to-one. This is a function, but what type of function is this one? One-to-one. Horizontal line test shows it's a one-to-one. So O to O. So one-to-one. This is a function, but which type? There's only two. So one-to-one or many-to-one? Many-to-one. Again, horizontal line test shows this is a many-to-one. So M to O. This is a function. What type? Many-to-one. Start to get the pattern? Yeah? Same thing with this one. Many-to-one or one-to-one? One-to-one. That's 5C, 5D. Cool? What I'm going to do now is I'm going to combine a bit of 5B with you as we're doing the questions together. Okay, so let's do this example here. Remember I told you about function notation? I'm going to teach you how to use function notation. So, just for now, I'm not going to explain what this is. This is called the code domain. I won't explain what that is yet. Just know in methods, it's always going to be R. Okay, so in methods, every time you do function notation, just write R there. Okay? Later on, I'll explain what that is. Domain, we said that that's all the x values you can take, and then you have to write f of x equals to whatever function you have. So take this example. This is my function. Instead of writing y equals x squared plus x, I'm now calling y f of x. Okay, so this f of x is the y. And the reason why we do that, just like our CAS calculator, means you can do things like f of 0, f of 2. So let's do it on the CAS, I'll show you. When you say f of 0, what does that mean? Let's have a look. I'm going to go to my CAS. I'm going to go menu 1, 1. I told you to do f of x. That's how I've been teaching you, right? X squared plus x. Why don't we use the y? It's because if you do f of 0, what this means is that you want to sub x equals 0 into the equation. That's what you're saying. So when you say f of 0, what you're saying is where the x squared is, I'm going to replace that with a 0. That's what you're saying. So the answer should be 0, right? But if you did it in this way, how would you have done it back in year 7, 8, 9, more like 9? 9 and 10 is you would say sub x equals 0. And you'd say y equals 0 squared plus 0. And then y equals 0. That takes too long. We try to condense that by using what we call function notation by just saying f of 0 and then equals to. We just tell you the answer. Okay, that's why we do that. So instead of using y, we just replace it with an f and it tells you what variable we're working with. Cool? So what would f of 2 be then? 6. Very good. Should be 2 squared plus 2. 4 plus 2 equals 6. Now what's interesting is when I put this in a test, I'll put another one. So I've got f of 0, f of 2. Most students will get that right. And I put this one in and they get it wrong. I say, what's f of a? What would you say? What was that? Who said that? Yeah, that's literally all it is. But funny enough, I put that in a test. Kids will get this one. They'll do 0 squared plus 0. 0. 2 squared plus 2. 6. And then I put an a. And they're like, no idea what to do. You do exactly the same thing. You replaced all the x's with the numbers, then why can't you replace the x with an a? That's it. It's just you put whatever's in that bracket, you're replacing the x with that. So I can do this one now. Let's test your understanding a bit further. What if I did f of a plus 1? What's that equal to? Yeah, that's it. That's all it is. It's just a plus 1 squared plus a plus 1. That's all it is. That's what it means. Yeah, so if I went back to my calculator and I did the same thing, if I just did f of a, literally, all it does is it just replaces the letter with a letter. Obviously, if I did a plus 1, it will do one up on me. It will actually expand and simplify. So it expands and simplifies. But if you actually expanded that, we should get the same answer here. Okay? So that's the idea. Whatever that bracket is, it's just a notation to simplify. Instead of saying sub this in, we're saving ourselves time from doing that. Does that make sense? Cool? All right. Now, you can read the function. Great. But notice, I have 0 to 2. What is that 0 to 2? What does that mean? What's this 0 to 2? What's that called again? It's not a quarter. Not a coordinate. This is your domain. Okay, now what is domain? You see, I'll show you on Desmos. If you were to sketch this graph, this is what it looks like. Desmos. Here we go, let's type it. F of x equals x squared plus x. That's a quadratic. We knew that. But can you see how it goes on infinitely? I can zoom out. All the x values can be taken. But when I say I only want the domain from 0 to 2, what you're saying is in that graph, I only want the x-axis to have 0 all the way up to 2. Part of the graph, only from 0 to 2. Nothing else. I don't want anything more than 2. I don't want anything less than 2. That's what the domain means. This is your domain. So if I go back to Desmos, how do you change that? For those who are Desmos savvy, you do the curly brackets and you say 0 less than or equal to for x, less than or equal to 2. Can you see how my graph had shrunk? That's 0 to 2 there. So if I zoom in, that's 0 to 2. Because I told it to only sketch on the x-axis 0 to 2. If I told it that I wanted to sketch from -2 to 2, so you get a bit more of the quadratic. That's from -2 to 2. If I said I want it from -3 to 2, you get the quadratic. If I said I want it from -infinity, then this will go on infinitely, but it stops at 2. This is your domain. You see what I'm doing? So what I'm changing is, all I'm changing is how much of the x do I want. I don't care about the y-axis. All I care about is the x. So the x-axis is called the domain. If you're only focused on the number line on the x-axis, that's called the domain. That's 5b. So 5b was about domain. What's range? It's the other way. The range is how much of the vertical axis do you want. But to get the vertical axis, you got to restrict your x. You restrict the x, you restrict the y. That's how it works. Because the y depends on the x, right? So here, just looking at this, if I go back to the 0, 2 again, what's my range? So on the y-axis, what's the smallest number and what's the highest number I can have? 0, 2, 6. And how do I get 6? Well, the endpoint, 2, clearly 2 squared plus 2, you told me before. F of 2 is 6. So the range is 0 to 6. My domain is 0 to 2. Does that make a bit more sense? That's what 5b is. So 5b wants you to write that to describe that. But then how do you describe it? 5a. 5a, you write the notation. So here's the notation. I want you to copy this down. So this is the proper way of writing notation. So that's what I mean by I'm combining 5a, 5b into 5c and d here. This is the graph. You guys understood that it goes up. We found that when x is 2, you figured out y was 6. We did it over here before. We know that when x is 0, y was 0. We did it over here before, right? Now, if they ask for domain and range, domain we already know from the question. This is how you write it. X, so it tells you that's the domain. Epsilon, that's the symbol for epsilon, which you've seen in your textbook. That means to be a part of. Okay, so for those who don't know it, write it down. This means a part of. So I'm saying the x coordinates on the x-axis is a part of. Now, what is it a part of? 0 to 2. So I would say this. 0 using interval notation. X is a part of 0 to 2. So when someone reads this, they know you're saying domain is 0 to 2. How do you think I'll say the range? What would I use? Y. So I do the same thing. Y is an element of, or epsilon, or is a part of, that means element, by the way. So element, the symbol is epsilon. So Y is an element of, what's my range? 0 to 6. So 0 to 6 is here. That's your range. So then you would write 0 to 6, and clearly you do include the 0 because there is a dot at 0, and there's also a dot at 6, so you include 0 to 6. That's how you write your domain and your range using set notations. Okay, so this is called set notations. That is interval notation. That's a set. So far, so good? So I'm really combining it. I'm doing 5B, 5C, 5D, but you can see how it's all related to each other. Let's test your understanding now. Go to the page with all the graphs. So go to the ones with the graphs. All right, let's test your understanding. So now you know what's a function, how to determine if it's a one-to-one function. I'm just going to delete this mess so you can see the graph better. Let's go. A. What is my domain? So X is an element of what? So look at this graph. There is no endpoints. It doesn't have a dot. So what is my x-axis values? What can it be? Negative infinity, because this 2 is on the y-axis. Okay, so we're only interested in the x-axis. What x values can this graph be? You see how every single x value has a point on the graph. So what's the other symbol that you've learned from 5a that says all values from negative infinity to positive infinity? What is that value? Capital R. So this is you saying that x can be any number. Can you see how it doesn't matter which number you pick? If you picked 100, there is always going to be a point on the graph. Okay, so that's what I'm saying. I'm saying this graph can have any x value. It goes on infinitely. But the range is different though. The range can't always be every single value. What's my range? What values can y be? So look at the y-axis. Ignore the x-axis. Just look at the y-axis. What's the numbers can y take? Then again. Very good. But because this is downwards, we have to say negative infinity to negative 2. Because it's the smallest value to the largest value. Can you see that? Can you look at the graph? You can see the graph only takes this section. Only these values of y will exist on the graph. This one doesn't. There's no points up here. So y can never equal to negative 1. Y can never equal to 0 because the graph doesn't even touch them. The graph starts from negative 2 as the highest point. And every single point you pick, it will relate to that point. Now, I did teach this back in year 2014. I taught a kid who absolutely has no understanding of algebra or anything, but I taught them this way. If you didn't understand domain and range, here's another way. It worked for this kid, right? If you want to know what the range is, this is what I taught him, because eventually he just didn't understand what I was saying. So this is what I said. I want you to draw horizontal lines. So if you're doing y, draw horizontal lines, because that's your y values, yeah? Keep drawing until you hit the graph. So he kept drawing, and every time he does this in this sack, he draws horizontal lines until he hits the graph. And then he goes like, I hit it, sir. I'm like, good. What value was that? And he's like, it's at negative 2. I'm like, great. So that's your largest value. And I'm like, I keep going until you find the end. And he keeps going. And then I say, so when do you stop? He's like, I can keep going. I'm like, great. So your largest y value is negative 2, but that means your smallest value is infinity. And he gets it. Versus x domain. So if you want domain, it's the other way. If you want domain is the x value. So you do vertical lines. So I told him, draw vertical lines until you don't get a graph or you don't hit the graph. So he draws it. He does that. He's like, I hit it, sir. I'm like, great. Find one where you don't. And he just keeps drawing it. And he's like, I hit everywhere, sir. I'm like, so then that means your domain can be anything. So then he learned that you can go negative infinity to infinity. So if that helps you, x is vertical lines and y is horizontal lines. Okay, so wherever it touches the graph, that's the maximum, and then wherever it keeps going, that goes infinitely. Let's try another one. Let's go to B. Think about vertical lines and horizontal lines. Let's go over here. So think about vertical lines. So if I ask you for domain, Domain. If you think about vertical lines, there's obviously a part where it hits the graph and there are parts that it doesn't. Where does it hit? Up to. What's the limit? Can you guys see it? What's the domain? 0 to? 0. Oh, actually, there's no number here. But can you see if I drew a vertical line? Starts here, so that's when x equals 0. But if I keep drawing, it keeps touching it up until whatever that point is. From here, it doesn't touch the graph anymore. So the domain must only be from here to here. Unfortunately, I don't know what that value is, though. I just know it's from 0 to whatever that number is. Does that make sense? So if I made up that number, if I said this was 7, then your domain would be 0 to 7. What about range? Range is horizontal lines. Can you try to picture horizontal lines cutting through? Where's my bottom number? What's my top number? Yeah. See, if I did horizontal lines, see, it doesn't touch the graph, doesn't touch the graph, doesn't touch the graph, but it touches that -2. That's the smallest number. And then the maximum number. So it keeps touching until you get to 2. So the range is only from -2 to 2. Only within that section that I actually hit the graph. That's called the range. Okay, so if I were to answer it, I would say y is an element -2 to 2. Starting to get it? Let's try another one. Domain. Range. Go, what's the domain and range? Hands up if you have an answer. Ben. Again, horizontal lines, because there's no caps, there's no dots here. You see, it implies it goes infinitely. So I can always draw a vertical line infinitely, and I will always touch the graph. So hence it's R. What about the range? R as well. Because it doesn't matter how I draw the horizontal line, it will always touch the graph. So that means there's a Y value for it. So hence, any number of Y and any number of X. Let's pick one where it gets you thinking a bit. I'm going to make up the numbers here. What else do you need to know? I think that's, and I'll do this one too. All right, let's start with this one. I put in some random numbers here. Domain and range. Domain, range. What's my domain? Is R. You guys see that? So for those who are sort of working at it, think about vertical lines. Draw vertical lines. It keeps going. I can always hit the graph. Now it doesn't show there's a dot here, so it doesn't stop there. That means the graph will keep oscillating, and it will keep going that way, and this graph will keep going that way. Right? So that means X, domain must be R. You can take any X value horizontally. Then, what about your Y values? This is a bit different now. What's my range? Hands up. What's my range equal to? Kai. Good. But remember, you always write from smallest to largest. So smallest to largest would have to be? Very good. So it has to be 0 being the smallest number, because clearly a horizontal line starts off. Smallest is 0 for the Y-axis. And the largest Y value has to be 4. So 0 to 4, and it's inclusive where you use close brackets if it's inclusive. So that graph there, you can see if I draw a horizontal here, it doesn't touch it. So that doesn't exist in the range. The range only literally touches the graph. Smallest value is 0. Largest value is 4. That's what domain and range means. So when you look at a graph, you're looking for where does it touch, and where does the X values exist, and where does the Y values exist. That's what domain and range means. Yeah. Ooh. All right, team. Do I have one more page for you? I think there was one more at the end. Was there? Or was that it? 1, 2, 3. Was there only 3? I thought there was another one. I don't have it on my digital thing. Oh. Why isn't it here? That's okay. Let's go. Maybe it's in this one. Cool. What's the domain? What's the range for this one? Someone different, someone new. New Muffy. For which one? For Y, very good. So the range, clearly, horizontally, starts off at -5, goes all the way to 4. So -5 to 4. What about your domain? What's my domain? Beautiful. Vertical lines. -2 to 2. So if you want to practice more of this type of question, that's exercise 5B. They might have different graphs. So parts where you don't include and some parts you do. Okay, but what I'm teaching you here, most of this will include. So just knowing how to read a domain and a range. Cool? Now I noticed that on your sheet, I've given you 2 problems for you to try. I want you to have a go at the back 2, looking at the graph for the first one, which I've given to you. State the domain and range and see if you can write it as a function notation. Okay, so I gave you gaps to fill it in. And then the second one, you might want to use a calculator to sketch it. Or if those who are inclined, you can actually do it without a calculator by looking at the properties of your equation. Okay, but if you need, use a calculator just to see if you can see the domain and range. And then write out function notation. I'm just going to insert it up on screen so that we can... Very good for getting that one correct. Have a go with the next one. Now, I didn't put a graph for you. There's 2 ways to do it. You can look at the equation itself. There's hints in the equation of what the domain and range can be. But if you can't see it, sketch on your CAS, and that should help you visualize what your domain and range should be. Be careful with this one. Worthwhile looking at this question. If you type it in your CAS, you will get this side of the graph. That's what it looks like. If you were able to analyze it, it's a fraction. If it's a fraction, it's more similar to a rectangular hyperbole, so you should have asymptotes. What's different? The square root. Square root of x, we know that you can't square root a negative number, so that means the x values, which is your domain can only be 0 or positive, right? But the problem is in a hyperbola, you can't have 0, because there's an asymptote at x equals 0. So your domain clearly should only be, just looking at the equation without even picturing it, I can already say you can't have 0 and it has to be all the positive values. So it's from 0 onwards, but don't include 0. So how do you write it? 0 is the starting point, but you can't have 0. All the way to infinity. So that means you can have 0.0001. You just can't have 0. You can have any other number between. And that's what the graph is showing. There's an asymptote. Here, the graph gets closer and closer. The x values are infinitely small, but it's not 0. So I'm saying it's starting at 0, but just don't include the 0. And it goes all the way to the right, which is infinity. Right? So you can either look at the graph, or you can look at the equation, and you can determine that root of x could only take positive numbers, and usually we say 0 to infinity. The problem is that x can't equal to 0 for a fraction. That's why this has to be an open bracket and not a closed bracket. Same thing with the range. Range, you can see there is a asymptote at y equals 0, so y can't equal to 0, but y can be any other number up here. So if you draw horizontal lines, you can see it will start from 0 to infinity, but don't include 0. So here the answer would be like that. Oh, you don't have to, because you've got it on the right side, so people know. But if it's a negative, you have to put a negative in front of it. Yeah. So here, there is another symbol if you didn't know. You could use R positive. Okay, so that means the same thing. So if you want to know a bit of set notations, R positive means every number that's positive, but don't include 0. That's R plus. So you can use R plus instead of an interval notation. And that's a quicker way to do it too. Okay, so here I would have wrote are positive, or you could write 0 to infinity open brackets, and the function is 1 on root x. Does that make sense? Okay, so I just showed you another notation. That means every number that's positive doesn't include 0. You can do R negative as well. It means every negative number except 0. All right, that was a big lesson today, but I think you guys got it.